Hello everyone. Hello. So we are live now. Okay. So this is the lecture 8 of our linear programming problem series, and this series is helpful for GATE exam, CSIR NET exam, and the state level SET exam. Okay. So in the last lecture we discussed the simplex method. Okay. So simplex method and the BGame methods and the what BGame method and one another method. So in this lecture we will cover the starting the duality. Okay, so duality, why you should read duality. So duality, to read duality, what our purpose. Okay, so the need for the duality, to read the duality, is what? So for some cases we are not get the solution in the primal problem. Here we introduce the name primal problem for the LPP. Okay, so I think live session is okay. Primal problem. Okay, is there any mistake? So and in this case the terms duals comes related to the primal. So what is the dual program, dual LPP? Okay, so every LPP, see, every LPP, suppose this is maximization problem, this can be the minimization problem also associated with the corresponding LPP of minimization problem or maximization problem. Then the original problem is called the primal and the associated problem is called the dual of the primal. That means what? That means suppose we have a maximization problem, then we should associate this maximization problem to a minimization problem. Okay, and if there are any minimization problem, then we can associate this minimization problem with a maximization problem. Okay, so if the given problem is the maximization problem, then this is called primal problem and this is called the dual problem, and vice versa case can be occur. Okay, so this is the case of duality in linear programming. Okay, so now let us comes to primal dual problem. Suppose let us consider the LPP maximum of Z, this is equal to C transpose X. Okay, if there is any mistake, then you can comment me in the comment section. Okay, so if voice, I think voice and other thing is okay, all okay. Okay, you can comment me once. So suppose subject to Ax equal to B, Z equal to C transpose X, and subject to Ax less equal to B where X greater or equal to 0. This problem is known as primal problem. Okay, and where A equal to, we know that A is an m by n coefficient matrix. Okay, and C equal to the cost matrix, that is C1, C2 and Cn. Okay, this is the cost matrix, and then B, this is the matrix B1, B2 and Bm, and X is the decision variables, and the X is the vectors of decision variables, and X is the matrix x1, x2, xm. Okay, so this is the what? This is the total primal problem. Okay, now we comes to the what? It's dual. How can we write the dual? So we define a minimization problem of the LPP and determine u1, u2 and um such that minimization of B transpose u subject to A transpose u greater or equal to C where u greater or equal to 0. See, here the problem is maximization problem, which is converted to a minimization problem first, and the cost matrix, the C and B are interchanged with a transpose. Okay, and we the new vectors which we introduced here in the dual problem is u. Okay, these are the decision variables in the dual problem, and here we write the matrix transpose of A, and these are the new dual variable, and this less equal to type inequality changed to greater equal to type inequality, and this B changed with the position with C. Okay, so this is the dual of the primal problem. So here some notes regarding the primal dual problem. Okay, so the case 1 is what? The dual of the maximization problem LPP is the minimum LPP and conversely. Okay, so dual of an maximization problem is minimization problem. Okay, so this is the first case. The number two is what? In general, the maximization LPP has the constant less equal to type of inequalities, whereas the dual problem has greater equal to type inequalities, that is greater equal to type constants. Okay, in general this case is happen, and another case also happen. Okay, so this another case may be happen. Okay, number 3 is the number of decision variables of the dual of the LPP is equal to the number of constraints in the primal LPP and vice versa. That means what? The number of decision variables of the dual is equal to the number of constant of the primal, and conversely you can say the number of decision variables of the primal is equal to the number of decision variables of the dual. Okay, so this is the case. Number 4 is the requirement vector of the dual problem is the cost vector associated with the objective function of the primal problem and vice versa. The requirement vector means this B vector. Okay, so the B vector of the dual problem is the cost vector associated with the objective matrix, and conversely that is the this is the case. Okay, so the cost matrix of the what? This cost matrix of the primal problem is the requirement vector of the dual, this one. Okay, so this is the case, and conversely. Okay, number 5 is the coefficient matrix of the constants of the dual LPP is the transpose of the coefficients matrix of the constant of the primal LPP. So okay, I think this is lagging, internet connection is okay. Now number 5 is the variables in both the problems are non-negative, that is if xi's are the decision variables in the problem and satisfying the non-negative conditions, and if ui are the decision variables in case of dual, then ui are also greater or equal to 0. So this is the case, and these notes are very important to change in case of to change a primal problem to a dual problem. Okay, and the conversely. Okay, and now here we take an example first. Suppose this is a primal problem which is a maximization problem. Okay, so the maximization of z equal to max z equal to 2x1 minus 6x2 subject to x1 minus 3x2 less equal to 6, 2x1 plus 4x2 greater equal to 8, and x1 minus 3x2 greater equal to minus 6, or x1 x2 are non-negative. Okay, so this is the case. Now what? First we convert this problem in the standard form. Standard form means maximization problem. For the case of maximization problem, what? The standard form is max z equal to suppose C transpose x and ax less equal to b. Therefore we convert this greater equal to type inequalities to the less equal to type inequalities, which is the standard form of an LPP. Okay, so max of z, this is equal to, we write 2x1 minus 6x2 with the subject to the condition x1 minus 3x2 less equal to 6, minus 2x1 minus 4x2 less equal to minus 8, and what? Minus x1 plus 3x2 less equal to 6. All three constants are of less equal to type. Therefore this is the standard form of an LPP. Okay, let u1, u2, u3 are the dual variables. Okay, so first the note is maximization problem converted to the minimization problem. Okay, so minimum of suppose w. Okay, now the what? The requirement vector of the primal problem convert to the what? Convert to the objective function, that is the cost matrix, cost vectors. Okay, so here we write 6, minus 8 and 6 as the cost matrix. Okay, elements coefficient of cost matrix, and the where coefficient of the constant of the primal problem is constant of the dual problem is what? This is the transpose of the matrix, that is this one. So 1, minus 2 and 1 is the coefficient for the first case. So 1 minus 2 and 1, so u1 minus u2 minus u3 is greater or equal to, this is the what? This is the cost matrix or cost vector in case of primal, and this is here the requirement vector. Okay, and that is the coefficient of requirement vector or matrix, you can say. And now the second one is, this is the second vector, that is minus 3 u1 minus 4 u2 plus 3 u3. This is greater or equal to minus 6. These all are less equal to type. Therefore in dual the constants are of greater or equal to type. Okay, so this is the standard what? Standard minimization problem. A minimum of w is equal to this with subjects to the constant. This A transpose u is greater or equal to b, or greater or equal to C transpose, you can say here. Okay, so this is the standard dual problem of the given primal problem. Okay, now let us comes to this theorem, which is an important theorem and basic theorems of duality, you can say. The dual of the following LPP, what? Minimization of Z equal to C transpose X, okay, X greater equal to B, or X greater equal to 0, okay. In the LPP, maximization of W equal to B transpose U subject to A transpose U less equal to C transpose for U greater equal to 0, okay. So this is the minimization problem converted to the maximization problem. See, minimize of Z convert to the max, minimization problem convert to maximization. Here the cost matrix, and in the primal problem is the what? Requirement vector of the dual problem, and the coefficient of A, this is equal to, we take the transpose of that matrix, coefficient matrix, and another changing is that this what? This is the requirement vector in case of primal problem, which is the cost vector of the dual problem, okay. So this is the case, this is the theorem. Now there is another theorem. The theorem says that this is very important theorem. The dual of the dual is the primal problem itself, okay. That means this is a very important theorem, and based on this theorem, in some year there are questions in GATE exam, okay. So dual of the dual is primal. Now let us see the table. Primal dual problem, okay. Primal dual problem. Primal dual problem, there are three types of primal dual problem, okay. One is symmetric type of problem, second one is unsymmetric type of problem, and third one is mixed type of problem, okay. So what is the symmetric case? If all the constraints are inequalities and all primal dual variables are non-negative, this is the case of symmetric primal dual problem, okay. The second one is if the constraints are equations, okay, and all the variables are non-negative, that is the primal variables and the dual variables are non-negative, this is the unsymmetric case. That means in this case, this is suppose Ax less equal to B type, and this is Ax equal to B type where all xi's are greater equal to 0, here all xi's are greater equal to 0, and the Ax greater equal to or can be inequalities, okay. So this is the case, and in this case this is also greater equal to type, you can say. So equations and inequality mixed, then this is unsymmetric, okay. And the mixed type, what? If the sorry, this one is the equations, okay, the inequalities are equations. And this, in the third case, if the constraint are inequalities and equations and some variables are unrestricted in sign, here the term unrestricted in sign is adds in the mixed type of primal dual problem, okay. That is why, that is what? Unrestricted in sign means xi greater equal to 0 or not equal to 0. This case is not provided with that variable or for this variable, okay. We don't know what is what if the variable satisfying the non-negativity conditions or not, okay. In that case we say that the variable is unrestricted in sign, okay. Now the theorem comes in, let us come to a theorem. If the kth constraint of the primal is an equation, then the corresponding dual variable is unrestricted in sign, okay. So we are giving examples for these theorems, okay. You can understand this theorem properly with the example, okay. Let us come to the example, just a minute. Then number theorem 2 is what? Just a minute. Just a minute. If this theorem says that if the kth constant, kth primal variable is unrestricted, just a minute, the pen is not working, okay. So if the kth primal variable is unrestricted in sign, then the corresponding dual constraint will be strictly an equation, okay. So this is the case. Now let us summarize these theorems, okay. Let us summarize this. So suppose the primal problem is an maximization problem and the dual problem is the minimization problem, then okay. Let us take the standard types of LPP, okay. So ith constant, if ith constant is less equal to type, okay, then the ith variable is greater equal to 0. if ith constant is equation like equations, then the ith variable is unrestricted in sign in the dual. Okay, if the jth variable is greater or equal to 0 in primal problem, then jth constant is greater or equal to type in the dual problem. If jth variable is unrestricted in sign in the primal problem, then jth constant is equations type. Okay, so this is the case of primal problem and dual problem. I will provided this PDF in the Telegram group or Telegram channel. You can collect this. Okay, so this is the case. Now let us take an example to understand the above theorems properly. Okay, so primal problem, this is, suppose let us take this primal problem. Okay, so minimization of z equal to, here we take an minimization problem. Okay, so which is I think it's easy to understand the theorems properly. Okay, subject to the constraint c x1 minus 3x2 plus 4x3, this is equation equal to 5. Okay, this is disturbing, just a minute. So this is suppose the primal problem, and this is the constant which is an equation. Then number 2 is the second constant is, this is an less equal to type inequality, and this is an greater equal to type inequality. Okay, so this is a best example to understand the above two theorems properly. Okay, because here we have equations, here we have less equal to type inequality, here we have greater equal to type inequality, and one condition is that the third decision variables is unrestricted in sign. Okay, so how we can solve this type of problems, or how can we write the dual of this problem? Okay, first it is given that since x3 is the unrestricted in sign, okay, then we put x3 equal to x3 prime minus x3 double prime. Okay, and retain the LPP in the canonical form. What is canonical form? We already discussed in the first or second lecture of LPP. Okay, so now we write it to the canonical form. Okay, so we write minimization of z equal to x1 plus x2 plus x3 dash minus x3 double dash. Okay, subject to the constraint x1 minus 3x2 plus 4x3 dash minus 4x3 double dash greater equal to 5. The canonical form of the minimization problem means mean z equal to what? Mean z equal to C transpose x, suppose, with the constant constraint x greater equal to b. This is the canonical form, I think, of the minimization problem. Okay, so therefore we write these equations with greater equal to type inequalities with a negative sign, and second one is we write the one equalities in two equations, two inequalities. Okay, with a negative sign. So we write minus x1 plus 3x2 minus 4x3 plus 4x3 double prime, 4x3 double prime plus 4x3 double prime greater equal to 5. This is only one equality equations. We write these equations with two inequations. Okay, or inequalities you can say. And minus x1 minus 2x2 greater equal to minus 3, and 2x2 minus x3 prime plus x3 double prime greater equal to 4. This is the inequality given in the above problem. Okay, so now we write the dual of this LPP. So dual means what? This coefficient, cost coefficients going to the requirement vector, and requirement vector going to the cost matrix or cost vector. Okay, and this coefficient matrix interchange, that is this coefficient matrix we write the what? Transpose form. Okay, a transpose form. So we write just this type of inequality. First we write the cost of the maximization problem. So minimization problem goes to maximization problem. Okay, and the cost, or my 5 u1 prime minus 5 u2 prime minus 3 u2 minus plus 4 u3. Okay, and then the equations or constants, how we write? So we write the transpose of the this coefficient matrix. Okay, so this we can write. So u1 prime minus u2 prime, you can write, see it properly. There is some I think technical issue हो रहा है यहाँ पे, ठीक है, क्योंकि ये लैग कर रहा है. ठीक है, so just see it. Okay, so u1 prime minus u2 double prime minus 2, this is less equal to 1. Since here the inequality is greater equal to, therefore here the inequality should be less equal to type of inequalities. Okay, and this is the maximization problem. The minimization problem, since this is the primal problem and this is the dual problem, therefore in the primal problem there are greater equal to type inequalities changes to the less equal to type inequality. Okay, and the second one is this, what you can write this vector. So minus 3 plus 3 minus 2 plus 2. Okay, so see the second constant, minus 3 plus 3 plus 2 plus 2. Okay, minus 2 plus 2. I think this will be minus 2 plus 2. This will be minus. Okay, so this is the case. And the third constant is this one, 4 minus 4 and 4 minus 4 0 minus 1. Okay, so 4 minus 4 0 means u2 is absent here, and minus 1, that is u3 less equal to 1. Since this here we get the coefficient 1 1 1 minus 1. Okay, so and these are the, sorry, the lagging here, 1 1 1 and minus 1. This is the cost vector of the primal problem, and here these are the what, requirement vector. Okay, and the third last one is what, minus 4 u1 prime minus plus 4 u1 double prime plus u3 less equal to minus 1. Okay, and all the variables here, u1 prime, u1 double prime, u2 u3 are all non satisfying the non-negative condition. Now we write the what, we write the u here, I think, just a minute, x3 is unrestricted in sign. Okay, so the third constant in the dual problem should be equation. Okay, so this is the equation, and we write therefore u1 equal to u1 prime minus u1 double prime, and write the dual and rewritten the equation. These equations are just okay. So this gives u1 minus u2 less equal to 1, minus 3u1 plus 2u2 plus 2u3 less equal to 1, and 4u1 minus u3 less equal to 1. Since the third variable is unrestricted in sign in the primal problem, therefore the third variable is equation in the dual problem. And since the first equation is first constant is equal, that is equation in the primal problem, therefore the first variable, that is u1 here, is the unrestricted in sign. Okay, so this is the content for today's session. I think this will be helpful for you. Okay, and sorry for the technical issue. I thought the live session going well, but there is some issue, the machine is lagging, or this is maybe the internet issue. Okay, so sorry for that. I think this session is very helpful for you. Okay, so if the session is helpful for you, then please give a like to this video, share it with your friends, and subscribe the channel. Okay, so thank you, मिलते हैं नेक्स्ट वीडियो में, बाय.